some problems on probability theory and on solving on hypothesis testing. And I prepared some problems from an older book that I used for this course. Let me bring the window properly inside the recording area. This was by Mario Triola's Essentials of Statistics. That's one of the actually best introductory books I've ever used and I've ever seen. It's not advanced at all. It's for people who want to understand the very basic concepts of probability theory and of statistics without any sufficient sophistication. Then, of course, at the point that we're doing the statistics part now, the inferential statistics, we're essentially pretty much at the level of this particular book. And if you really want to have a second book to have some help with statistics, that's a very good choice. So I'm actually, to pay the credit to the author, I'm going to write the title of the book, Essentials of Statistics by Mario Triola. So we will solve some problems from this book, and then we'll also look at some problems from our book. Let's look at the following problem that I have here. In New York Times, problem number 24. So a New York Times article noted that the mean lifespan for 35 male symphony conductors was 73.4 years, in contrast to the mean of 69.5 years for males in the general population when that was taken. Assuming that the 35 males have lifespans with a standard generation of 8.7 years, use a 0.05 significant level to test the claim that male symphony conductors have a mean lifespan that is greater than 69.5 years. Actually, this question, and this is very important, can be phrased in the following way. Does it appear that male symphony conductors live longer than males from the general population? So that leads to the following hypothesis. Do male symphony conductors live longer than males from the general population? Okay, here are a few possibly problems with this. If we go to the random sample to test to see whether these 35 male symphony conductors are a random sample among male symphony conductors. First, we have to see where these people live. We don't have any good information about that. Second, we need to see which are the periods that cover their lifespan. Have they all died recently, or have they died in a time interval which is basically like 50 years? Because what applies now and what applied 50 years ago are not exactly equivalent. Therefore, in this case, if we have such a big time span for the collection of the data from those 35 male symphony conductors, the big problem that would arise is that the sample is not representative of the general population. And in fact, the sample is not the random variables x1, x2, xn in the sample are not all identically distributed. Suppose that none of these problems exist because, well, we just have the information here and we can't use it. We can't check whether any of these claims that I'm making are true or not. Suppose that everything is fine and these 35 male symphony conductors are truly a random sample. The question is the statement valid or not? And to that effect, we will conduct a little bit of our study. So let's proceed as we must do in a typical hypothesis testing problem. So what is the random variable we want to examine here? Is lifespan. Let's look at our. Let's look at the statement. Does it appear that male symphony conductors live longer than males from the general population? So X is lifespan of male symphony conductors, and we're looking at the their at the mean. Okay. Now, in general, there is and you should look at the phrasing here. Does it appear that male symphony conductors live longer than males from the general population? This phrase at no place mentions the word in average. But the way it is being phrased, it's a categorical statement, so it applies to all of them. So it does refer to the average. So it's a statement about the mean of x, and the statement about the mean of x, which is my next step, I have to formulate my hypothesis in mathematical terms, is that the mean of x is greater than 69.5. So that's what we want to test. That's the hypothesis we want to test. And therefore, we have the following alternative hypothesis. Mi sub x is greater than 69.5, and that the mean of x is equal to 69.5. One might have said take less than or equal to, but in the working case, when you work the case, when you do the math, you take only the equality. That's why we put the null hypothesis to have the equality only. Now let's see. Let's see what is the second question. Why doesn't the experience of being a male symphony conductor cause men to live longer? That's another question, but I'm not going to deal with this. I'm going to deal only with the main one. So 35 males have lifespans with a standard deviation of 8.7 years. What does that mean? That standard deviation is sample standard deviation. So we know that the sample standard deviation of these 35 people is 8.7 years, and the sample mean is 73.4 years. So we have a sample size of 35, which is greater than 30. So we can assume, or we don't need actually to assume anything about the distribution. in particular normality, about the distribution of X. Actually not about, for. And we also assume that the sample we have is assumed to be random in absence of any specific statements for the collection of the data. Now let's see, what kind of test do we need? We want to test that mi sub x, the mean of x, is greater than 69.5. So we need a right tail test based on the type of the alternative hypothesis that we have. What is the test statistic that we will use? Well, here, since n is greater than 30, you can use either z or t. You can use both. T is necessary when you have sample sizes smaller than 30. You have to have t, and x, your random variable, should be normally distributed. When you have a random sample greater than 30, you can use, and you believe that the data have approximate normal distribution, you can use t. Otherwise, you can use z. Either way is acceptable by me. I would use z though, since I have made no assumption, no specific assumption about the distribution of x. Since you haven't argued about the distribution of x, it's better to go with z, because z comes from the use of z comes from the central limit theorem, and the central limit theorem is distribution agnostic. So my z statistic is equal to x bar minus the mi sub 0. What is mi sub 0 here? Well, we mentioned mi sub 0 already. That's mi sub 0, 69.5. The average lifespan of the general population, divided by S, the standard deviation divided by N. We can use S instead of sigma because N is greater than 30. So let's calculate what is the value of the z statistic. These guys are 73.4. Okay. So if we do our calculation, this is 2.652. Now, the significance level has been set by the problem to be equal to 0.05, and we want a right tail test. So the critical region should be on the right. The critical point, which is Z1 minus the 0.05, so that would be 0.95, is equal to, make it my tables, and I'll be back to you. Um, the critical point is so this point is 1.645. So if we compare our findings, that's the critical point. Our finding is 2.652. The value, as I call it, of our statistic, as you see, we used the Z statistic, and that's the value. So we compare the value of this statistic with the critical value. The critical area is to the right of this 1.645 because we do a right tail test, and therefore, since since Z of, that's the best way to write it, of 0.95 is less than the value of our statistic, 2.652, we reject the null hypothesis, and therefore, now the final step is to phrase our result, our finding, in simple language. It appears that symphony conductors live longer, in average, I would say in average, live longer than the general population. So that's the statement that we did. And that completes the solution of this problem. So as you see, we have the following stages for the solution. First, we try to understand what is the random variable we're talking about and what is the parameter of the random variable. The hypothesis will be in investigating, and then we formulate our two hypotheses. First, we start with the alternative, and then based on the alternative, we take the null. We formulate the null hypothesis. Then we look for our sample size. The sample size is critical for the choice of our test statistic. If the sample size is less than 30, then we have to use the t statistic, and of course, in order to do that, then we need to check one more assumption. Is X the random variable which we have identified for this problem normally distributed or not? That's the critical question there. If we want to support or to investigate a little bit, if it is to get an idea if it is normally distributed, we can use the data, if the data are given to us, to form a box plot. After we have done this and we have located which statistic we use, we just do the math here. We found the critical point, and finally we compare the value of the test statistic, which is the test statistic here is Z. We compare the value of the test statistic, this one, the 2.652 in this problem, with the critical value. And if the value of our test statistic, since we do a right tail test, is greater than the critical value, then we reject the null hypothesis. So finally, we phrase our finding in simple language. That simple language pretty much looks like the formulation of the hypothesis that we are testing, but in this case, it's not stated as a question, but it's stated as a conclusion. I guess that must have been a very instructive example here. Let me do another one I want to talk about. Let's do the last example, the second example, number 25. Listed below are measured amounts of lead in the air collected by the EPA at Building 5 of the World Trade Center on different days after September 11th. So there are certain stations that have recorded certain values. Now, the critical value, no, the important value for health is 1.5 micrograms per cubic meter of air. That's the EPA standard. The question is, do the data that we have below suggest that the air, if following the attacks of September 11th at the World Trade Center, were polluted with lead at unhealthy levels? Now let's look at the data. Let's copy these data points. I will order these data points. So I do the so-called order statistics. And finally, we have a huge value, 5.4. Let's do the histogram. Let's do the box plot here. The smallest value is the 0.42. So I have it on the left. We don't have many data points. We have very few data points. So we have 1, 2, 3, 4, 5, 6 data points. So 6 divided by 4 gives you 1.5. So somewhere in between these two, we have the median. And then we have 3 points here, so I will pick, this will be my first quartile. Clearly, my third quartile is 110. My first quartile is 0.48, and my median is, I will take the average between 0.73 and 110. I use as 0.92. That's clearly somewhere here, 0.92. Finally, we have a huge value. Let's say somewhere here, the maximum value, 5.4. So that's the box plot for this data. Clearly, from the box plot, we infer that the data do not support the assumption that X, which is lead concentration over at the World Trade Center after 9/11. X does not appear to be normally distributed. At least you have that X probably is bimodal. So what can we do in this particular case? First of all, we have very few data. So there are two ways we can act. Since the sample size n is 6 and normality is critical, for the accuracy of our results, or for their reliability, it's better to say for their reliability, we can do two things. Both are legitimate. Either abandon the study and say we don't have enough data, we need to collect more data, or if we can collect more data, that's the data, we have to make an assessment. We must caution about the validity of our assessment. So let's proceed with the fact that, let's say that X so although this doesn't appear to be supported by the data that we have, we will make that assumption. We have already argued and we said, well, there are two things that we can do. Either I don't say anything, I don't know anything, I need more data, or I at least try to see what do the current data suggest, if all of these data are reliable. If all of these data are reliable, then there's a third option, possibly. One measurement is wrong. Which can possibly be the wrong measurement? This. But, because why? You could call this an outlier. It's very far from all of the other measurements. The other 5 measurements, come close to be correct, to have some consistency, some reasonable consistency among them. But this one is an outlier. Is the outlier true, or is it the result of an error in the measurements? If we treat this as an error in the measurements, then we should typically disregard it and proceed with the other measurements that we have. And in this case, of course, the situation will change a little bit. because it will push that median to the left, and now things will look more normally distributed. All of a sudden, 0.73 will become the median. If this is not an outlier but is a true measurement, then it indicates that there is something very bad going and only one of our stations detected it, so we truly need more measurements. Let's see what the results will give. So n is 6, so we must use the t-statistic. Okay, so I need to summarize a little bit. I don't think that we completed this. So this is what I would have written if I had to make a right statement. Either we treat 5.4 as an outlier, or if it is not, then we need more data. We need a bigger sample. In any case, our results should be used or should be considered as non-definitive. That's a nice statement. So what is the t-statistic now? What does the t-statistic tell us? Okay, well, here we need to do all the entire job, work with everything. So we need to find S, the sample standard deviation, 1, 6 minus 1, is 5. And we also need to have X bar, so let's calculate this. So this is our S square. So what is S? S is the standard deviation. So 2.6, 2.06 is S. So our t-statistic now is X bar minus the EPA standard, which is 0.15. Yes, 0.15. Divided by S, divided by the square root of 6. And all of this gives us 0.02. Let's do the computation one more time. So this is the value of our t-statistic. Now, what kind of test do we need? We need a left tail test because our assumption, oh, I forgot to, sometimes I preach to the choir, and I don't keep. Our alternative hypothesis is that the mean of x is greater than 1.5, and the alternative, the null hypothesis will be, of course, that the mean is equal to 1.5. So we need a right tail test. The t-statistic that we have is value 0.205, and for the level of significance that we want, which is 0.05, we have 5 degrees of freedom. The value of the critical one tail test, the critical right tail test, the critical value for the right tail test is 2.015. So this is exactly the value t, 0.95, comma 5. This is 1 minus alpha, and this is the number of the degrees of freedom we have. And of course, that is true. Therefore, what we have is that h sub 0 is accepted, which says that the data suggest that the lead concentration in World Trade Center immediately after 9/11 does not exceed EPA maximums. If we consider the value that was very big as an outlier, of course, then we remove it from the data, then this example is even more exacerbated, but we have to see that a little bit. So then what you can say is that, of course, this is a result that has happened, that can be derived if you take into account all of the considerations and the reservations we have expressed earlier about the nature of the data and the validity of the data. Now, if the 5.4 measurement is removed from the data, then X appears to be normally distributed. The sample size is small, so I can use I can use the t-statistic again, and this time the t-statistic will have the following value. Things will change a little bit because what changes is that these numbers, all of these numbers change. So let's see what would be the new numbers. So if now we exclude, by excluding the outlier, the numbers change significantly, so x bar becomes 0.73, which actually is equal to the median. That's one very strong evidence that the data have a normal distribution. and everything comes out to a t-statistic, which I don't really need to calculate because it's negative, but since I'm doing a right tail test, the critical value is a positive number, so we accept the null hypothesis as true, which essentially leads exactly to the same conclusion as previously. So with or without this strange measurement, the 5.4 measurement will have the same result. Now, what is the problem that arises? This 5.4 measurement may be just one measurement, but if it is not wrong, it only says one thing, that there is a pocket of lead pollution somewhere, which requires, in order to be verified scientifically, the collection of more data. Where from? Probably from the vicinity where this measurement, this off-the-charts measurements has been collected. And this is the proper way we should direct the research. We should not then be content with this result that everything is fine because statistics say so. Statistics say so, but statistics say so that because they don't have enough data. You see, with this value or without the value, the conclusion is still the same. But what if this value is not just an isolated or it's just one isolated value, but it indicates a concentration of lead that has gone undetected because we don't have sufficient measurement devices deployed in the region. So the final problem I want to talk about has to do with the power of a test. So let's calculate the power of a test. Actually, I think I have my marker somewhere. So let's do problem 5.7. So which we have that x has a normal distribution. Actually, we are given here the variance. We have the following to test. That's the null hypothesis, and that's the alternative hypothesis. So the problem says the criterion for rejection. What type of a test do we need? We need a right tail test. So this is a right tail test. So the criterion for rejection is x bar is greater than or equal than c. Let me mention something here. We have used z or t, and we say the criterion for rejection if z comes greater or t comes greater than the critical value. Well, this is how this thing works. X bar, let me show you what c is. X bar minus 32 divided by sigma, which has been given to us the square root of 40 here, divided by the samples, the square root of the sample size, is greater than or equal than the critical value. The critical value is okay. Now you don't know what the critical value is. Is alpha, is 1 minus alpha. And we'll use a sample size, a sufficiently big sample size. We'll see z or t 1 minus alpha comma n minus 1. So we'll see which one we'll take. Now, what is alpha here? Alpha, how can we detect? How can we find alpha? First of all, if you look at the problem, what the problem uses operating curve, the value at me equal 32 or 30, let's say 36 or whatever, me sub x. This is a value for the alleged mean, and the main idea is what is the type 2 error, what is the probability. This is the probability that we reject, we accept the null hypothesis, we reject the alternative, given that the mean is different, in particular equal to 0.36. If this is done, this is a type 2 error. And this type 2 error, the probability for this type of 2 error changes as this mean changes. And that value, OC of me 36, that's the power of the test, which we denoted by vita, and that's the correct notation, not the OC, vita at 36. So this is what I'm calculating. Look, the book is giving you vita of 32. It says OC of 32 is equal to 0.9. And you remember yesterday, you remember from the part of the lecture that actually that had these that I showed you the curves. It's up here. That when, so this is, let's say that this is the 36 here. When this slides and goes into, that mean falls onto the mean, the alleged mean, the one that is given by the null hypothesis, then this area, which is the yellow, coincides with the area which is to the left of this value, which is the critical value. The area to the left of the critical value is always 1 minus alpha, because the area to the right of the critical value is equal to alpha. That's, of course, for the right tail test. And therefore, since I have this right tail test, and I'm given the value at 32, which is the mean that the null hypothesis gives, this 0.9 is the level of confidence. Which is the 1 minus alpha, and therefore my alpha is the 0.05. So I found the alpha, because without the alpha you cannot calculate the power. You need the alpha in order to calculate the power. So now let's look what is the calculation for this beta of 36. We start from here. When do you accept H sub 0? You accept H sub 0 if x bar is less than or equal than the critical value, which here is C. That's the criterion for acceptance. And what is the type 2 error? You will do this given the fact that μ is equal to 36. So in this calculation, the calculation of the power we take as an event that we accept the null hypothesis. So the valid criterion is the criterion for acceptance of H sub 0. Here is X bar is less than or equal than C. And the condition is that the true mean is 36 and not the alleged 32. H sub 0 means that the mean is 32. That's the error. So what is this actually equal to? How are we going to find it? Well, let's see what we need and if we actually need any of these here, because I didn't show you how to find C. You will see that in the process, but because to find C, I will essentially use this formula. You will see now. So I do my, as I would call it, my standardization here. Notice that the problem gave me the variance sigma square equals 40. So, and I know that X has normal distribution, so X bar has also normal distribution. And this is because X has normal distribution. Therefore, this new random variable here is Z and has standard normal. And I realized that I made a mistake. I was talking for some reason about 36, but it's 35 actually, the value. And I'm given the power of the test. It's at 35. It's 0.15. What I want to find is the sample size that will guarantee that the power of the test is 0.15 when μ is equal to 35. So this is the probability that Z is less than or equal than this C divided by n. Now, since μ is 35, that conditional probability is exactly, since the true mean is 35, it's then that X bar minus 35 minus this true mean has standard normal distribution. Without this being equal to 35, if I subtract 35 from X bar, I will not have a normal distribution, the standard normal distribution for the Z. So here I'm getting at this step rid of this assumption. I don't need it anymore. I applied it. This has standard normal. So what is this? This is equal to the distribution function of the standard normal divided by this. And that should be equal to 0.15 from this. Now, what is equal to 0.15? What is the point of the standard normal distribution which is equal to 0.15? Let's see here. Let's look at the table. It is actually, I would put it negative to 1.35. No, 035. That's what it is. So here I have one equation for C and for N. What should be my other equation? The probability that we accept given that mi is equal to 32, that was 0.90. We were given that, and that's exactly the OC32, or beta of 32. And this is, we mentioned that is 1 minus alpha, because this is equal to mi sub 0. But let's do the standardization we did before here. So that's Z, which has standard normal, so we know that C minus 32 is equal to 0.9. What is the 90th quantile of the standard normal distribution? Well, we'll look at the tables again. And we'll look at the tables, and the tables say that this is actually 1.285. So using this equation, 1, and using this equation, 2, we can actually find C, and then we can find the sample size that we need in order to achieve these two powers, these two values. Now, to find the, as you understand, to find C, you simply need to divide both of them and that actually will give us C, this equation. And after we put that, after we find C from this equation, we can very easily find an estimate for N. Now, if N has to be a positive integer number, therefore, if you don't find a positive integer number, just take a bigger, slightly the next bigger value, the next bigger integer value. And with this, we conclude.